A capacitor is formed by two rectangular metal slabs or metal plates. A capacitor is formed by two rectangular metal plates of area A, separated by a distance d, separated by a distance d. A capacitor is formed by two rectangular metal plates of area A, separated by a distance d. Dielectrics of dielectric constants K1 and K2 are filled diagonally in the gap between the two plates. Dielectrics of dielectric constant K1, K2 are filled diagonally in the gap between the two plates. Find the capacitance. Dielectrics of dielectric constants K1, K2 are filled diagonally in the gap between the two plates, and we have to find the capacitance. This is a diagram of parallel plate capacitor in which two rectangular plates are separated by a distance. Now we are denoting the two rectangular plates which are separated by a distance d. This is a rectangular metal plate of the capacitor. This is a rectangular metal plate of the parallel plate capacitor. And we can denote another rectangular plate, and this is another rectangular plate of this parallel plate capacitor. D is the distance between these two rectangular plates of this capacitor. D is the distance or intermediate distance between the two parallel plates of the capacitor. The gap between the two rectangular plates are filled with two dielectric media diagonally as shown in the figure. K2 and K1 are the dielectric constants of the dielectrics placed diagonally between the two rectangular plates of a parallel plate capacitor. So this is a dielectric medium of dielectric constant K2. This is a dielectric medium of dielectric constant K2. Dielectric constant K2. We can denote another dielectric medium of dielectric constant K1. This is the dielectric medium. This is the dielectric medium of dielectric constant K1 of dielectric constant K1. And these two dielectric media are placed diagonally between the two rectangular plates. Now we consider a small element of these two dielectric media. This is the small element of width dy. We can denote, so we have to denote this small element. This is the small element of dielectric medium of dielectric constant K2, and also you can denote small element or elementary portion of the dielectric medium of dielectric constant K1. This is the elementary portion or small element of this dielectric medium of dielectric constant K1. This is the small element of this dielectric medium. This is the small element of this dielectric medium. L is the length or height of the rectangular plate. L is the length or height of each rectangular plate of this parallel plate capacitor. So here L is the length or height. We can denote the capacitance of the small element of dielectric media of dielectric constant K1 and K2. dC2 is the capacitance. dC2 is the capacitance of the small element of dielectric constant K2, and dC1 is the capacitance of the small element of dielectric constant K1. dC2 and dC1. This is the diagonal along which two dielectric media are placed in the gap between the two plates, and this diagonal makes an angle theta with the vertical direction, and this angle is also theta. Height of the small element is dy. dy is the height of the small element. We can denote the length of this portion, that is y, and also we can denote the length of the horizontal portion. X is the length of this horizontal portion of this triangle, y and x, and also here y equal to 0 at the lowest point and y equal to L as the highest point of each rectangular metal plate. We can denote the width of each rectangular plate. Here B is the width. B is the width of a rectangular plate. The gap between the two plates of parallel plate capacitor, the gap between the two plates of a parallel plate capacitor is filled diagonally with the two dielectric media of dielectric constant K1 and K2 of dielectric constants K1 and K2. Again, we can show in what way the gap between the two rectangular plates are filled with two dielectric media diagonally. This is the diagonal, and two dielectric media are placed in the gap diagonally as shown in the figure. This is a dielectric medium of dielectric constant K2, and we have another dielectric medium which is placed in this way, and this dielectric medium has dielectric constant K1. So that means the gap between the two parallel plates of the capacitor is filled with two dielectric media of dielectric constants K2 and K1. The dielectric medium of dielectric constant K2 exists on the left hand end of the capacitor. D is the separation between the two plates, and these are the two dielectric media placed diagonally in the gap between the two parallel plates of the capacitor. Here we have to find the equivalent capacitance C. In the diagram, dC2 is the capacitance of small element of dielectric constant K2, and here we can write down the expression of dC1. dC1 is equal K1 epsilon 0 B dy divided by x. B dy is the area of cross section of the small element of dielectric constant K1, and dC1 is equal to K1 epsilon 0 B dy divided by x is the capacitance of the small element of dielectric constant. Capacitance of small element of dielectric constant K1. dC1, in the diagram we can denote dC1 is the capacitance of small element of dielectric constant K1. This is the small element, and dC1 is the capacitance of this small element of dielectric constant K1. dy is the height. dy is the height of the small element. dy is the height of the small element of dielectric constant K1. and width of this element is b. Small b is the width of the small element or elementary portion of this dielectric medium. Again, here in the diagram, A is equal to B dy. Area of cross section of this small element is dA. It should be dA, not A. dA is equal to B dy. B dy, or area of cross section of this small element. This is the cross section of the small element of dielectric constant K1. And height of this small element is dy. Height of this small element is dy, and area of this small element is A, which is equal to B dy. B is the width and dy is the height. Similarly, you can write down the expression of dc2, which is equal to K2 epsilon 0. dc2 is equal K2 epsilon 0. Here we can denote x is the width of the small element of dielectric constant K1 having capacitance dc1, and dc1 is equal to K1 epsilon 0 B dy divided by x, and dc2 is equal K2 epsilon 0 B dy divided by d minus x, where B dy is the area of cross section of this small element of the dielectric medium of dielectric constant K2. dc2 is the capacitance of the small element. dc2 is the capacitance of the small element of dielectric constant K2. So in the diagram, you are denoting the small element which has the capacitance dc2, and width of this small element is d minus x. D minus x is the width, and height of this portion is dy. Now in the expression of dc1 and dc2, we have dy. That means it will be integrated with respect to dy. But in the denominator of the expression dc1 and dc2, there is x. In dc1 it will be integrated over dy, but in denominator we have x, and also in dc2 it has dy, but in the denominator it has x. That's why we have to express x in terms of y. Now the gap between the two parallel plates is AB C prime D prime. Now the horizontal portion of the small element of dielectric constant K1 is NP. NP is the small horizontal portion of the small element of dielectric constant K1. And the diagonal BD prime makes an angle theta with the vertical. The diagonal BD prime or BP, the hypotenuse BP of the triangle BNP makes an angle theta with the vertical. Similarly, the diagonal BD prime makes an angle theta with the vertical edge D prime A. From triangle BNP, tan theta is equal x by y. Again, from the triangle BAD prime, tan theta equal d by L. Tan theta equal d divided by L, where d is the distance between the two parallel plates and L is the length of or height of each plate. D is the perpendicular and L is the base of the triangle BAD prime with respect to the angle theta. Comparing this, we get x by L equal to d by x by y is equal d by L. or comma x is equal d by L into y. X is equal to d by L into y. D by L into y. Therefore, d minus x is equal to d minus d by L into y, or comma d minus x is equal L minus y divided by L into d. L minus y divided by L bracket closed into d. That is the expression of d minus x. D minus x is equal L minus y divided by L into d. Putting this expression of x and d minus x in the equations 1 and 2, putting the expressions of x and d minus x in the equations 1 and 2, we get dc1 as equal k1 epsilon 0 b dy divided by d by L into y. D by L into y. dc1 had the expression k1 epsilon 0 b dy divided by x. Now putting the expression of x, we get d by L into y. Putting the expression of x as d by L into y, we get dc1 as equal k1 epsilon 0 b dy divided by d by L into y. Therefore, dc1 equal k1 epsilon 0 L dot b dy divided by d into y. K1 epsilon 0 a divided by d dy by y. That is the expression of dc1. dc1 equal k1 epsilon 0 a divided by d into dy by y. So in the picture, these are two parallel plates of a parallel plate capacitor. L is the height of each plate and B is the breadth. B is the width. B is the width of each plate. Area of cross section is L dot B. Area of cross section of each plate is A equal L dot B. Small d is the separation between the two plates. An intermediate gap is filled with two dielectrics diagonally as shown in the figure. In this case, the gap between the two parallel plates is filled with two dielectric media of dielectric constant K2 and K1. Similarly, DC2 equal K2 epsilon 0 b dy divided by d minus x. It was d minus x. Now in place of d minus x, we can put L minus y divided by L into d into y equal K2 epsilon 0 b dy. L minus y divided by L into d K2 epsilon 0 L dot b dy divided by L minus 1 into small d equal K2 epsilon 0 a by d dy by L minus y. This is the expression of DC2. This is the expression of DC2. Therefore, DC2 is equal K2 epsilon 0 divided by d into dy by L minus y, where area of cross section of each plate A is equal to L dot B. Now this capacitor, parallel plate capacitor containing two dielectric media placed diagonally, can be assumed as the series combination of two capacitors containing two dielectric media of dielectric constant K2 and K1. DC2 and DC1 will appear to be connected in this series combination. DC2 and DC1 will appear to be connected in the series combination. Therefore, the equivalent capacitance of this series combination of two capacitors of capacitances DC2 and DC1 is the equivalent capacitance of the series combination of the two capacitors DC2 and DC1. On the left hand there is DC2, then DC1 is connected, is equal, is DC equal DC2 into DC1, DC2 into DC1 divided by DC2 plus DC1. This is the equivalent capacitance of the series combination of two capacitors of capacitances DC2 and DC1 equal. Putting the expression of DC2 and DC1, we get K2 epsilon 0 A by D into dy by L minus y into K1 epsilon 0 A divided by D into dy by y whole divided by K2 epsilon 0 by D dy by L minus y plus K1 epsilon 0 A by D dy by y equal K1 K2 under bracket epsilon 0 A divided by D whole square, epsilon 0 A divided by D whole square, dy square into L minus y into y into 1 divided by L minus y into y. In the denominator, epsilon 0 A by D into dy, bracket opened, K2 divided by L minus y plus K1 by y is equal K1 K2 epsilon 0 by D into dy divided by y into L minus y divided by y into L minus y K2y plus K1 L minus y, K1 into L minus y. Therefore, DC equal K1 K2 epsilon 0 A divided by D dy divided by K2 minus K1 into y plus K1L. Therefore, DC equal to K1 K2 epsilon A divided by D dy divided by K2 minus K1 y plus K1L. This is the equivalent capacitance. This is the equivalent capacitance of two small elementary capacitors of capacitances DC1 and DC2. Equivalent capacitance of two small elementary capacitors of capacitances DC1 and DC2 in series combination. This is a parallel plate capacitor. The gap between the two plates are filled with two dielectrics diagonally, and DC2 is the capacitance of elementary portion of dielectric constant K2, and DC1 is the capacitance of the elementary portion of dielectric constant K1. And DC2 and DC1 appear to be connected in series combination, and the equivalent capacitance of this series combination is DC. Therefore, the total capacitance of the parallel plate capacitor is equal C equal integration 0 to L DC equals 0 to integration 0 to L K1 K2 epsilon 0 A divided by D dy divided by K1 L plus K2 minus K1 into y, K2 minus K1 into y equal. Now constant terms can be brought outside integration. K1 K2 epsilon 0 A divided by D integration 0 to L dy K1 L plus K2 minus K1 into y equal K1 K2 epsilon 0 A divided by D log base C bracket open K1 L plus K2 minus K1 into y divided by dy of K1 L plus K2 minus K1 into y bracket close, third bracket 0 to L, third bracket 0 to L equal K1 K2 epsilon 0 A divided by D log base C K1 L plus K2 minus K1 y divided by 0 plus dy K2 minus K1 dy K2 minus K1 into y, third bracket closed 0 to L, 0 to L. equal K1 K2 epsilon 0 A divided by D. In the numerator we have log base E K1L plus K2 minus K1Y. K2 minus K1Y bracket closed divided by K2 minus K1. If we differentiate K2 minus K1 into Y with respect to Y, we get K2 minus K1. K1 K2 divided by K2 minus K1 bracket closed. Epsilon 0 A divided by D bracket open log base E K1L plus K2 minus K1 into L bracket closed minus log base E K1L plus K2 minus K1 into 0 bracket closed. Putting upper limit L in place of Y, we get the first term log base E K1L plus K2 minus K1 into L. Putting lower limit 0 in place of Y, we get the second term, that is log base E K1L plus K2 minus K1 into 0 equal K1 K2 divided by K2 minus K1 bracket closed epsilon 0 A divided by D. Log base E K1L, if we simplify, then we get log base E K2L minus log base E K1L. Log base E K2L minus log base E K1L bracket closed equal K1 K2 divided by K2 minus K1 bracket closed epsilon 0 A divided by D log base E under bracket K2L divided by K1L bracket closed. Finally, we get the expression of C, which is equal to K1 K2 divided by K2 minus K1 epsilon 0 A divided by D log base E K2 by K1 bracket closed. This is the expression of capacitance of a parallel plate capacitor in which the gap between the two plates are filled with two dielectrics diagonally. This is the capacitance of a parallel plate capacitor. Parallel plate capacitor in which the gap in which two dielectrics or two dielectric media of dielectric constants K1 and K2 are filled or are placed diagonally in the gap between the two plates. We consider the gap. This is the gap between the two parallel plates. This is a parallel plate capacitor. D is the distance between the two parallel plates. This is the second metal plate. We can denote the first metal plate. They are rectangular plates. D is the distance between the two rectangular plates. Now, a dielectric medium. This is a dielectric medium which is placed diagonally in the gap between the two plates. This is the dielectric medium which is placed diagonally between the two plates, which has dielectric constant K2. We can place another dielectric medium in the same way, that is, this dielectric medium is placed diagonally between the two plates, and this dielectric medium has dielectric constant K1. This is the area of cross section of each plate, or cross sectional area. Width of each plate is B. Small b is the width of each plate. L is the height of each rectangular plate, and area of cross section of each plate is A equal L dot B. Now the dielectric medium of dielectric constant K2 is placed in contact with the positive plate of the capacitor, and another dielectric medium of dielectric constant K1 is in contact with the negative plate of the capacitor. A dielectric medium of dielectric constant K2 is placed in the left portion of the gap between the two plates diagonally as shown in the figure. This is the dielectric medium of dielectric constant K2 which is placed diagonally in the left portion. Similarly, another dielectric medium of dielectric constant K1 is placed in the right portion of the gap between the two plates, and C is equal to Q1 K2 divided by K2 minus K1 epsilon 0 A divided by D, epsilon 0 A divided by D log base C, that is ln K2 by K1, K2 by Q1. C equal K1 K2 divided by K2 minus K1 epsilon 0 A divided by D log base C K2 minus K2 by Q1, where K2 is the dielectric constant. K2 is the dielectric constant. K2 is the dielectric constant of the dielectric medium. Dielectric medium which exists in the left portion, of the gap, between the two rectangular plates, or this medium is also placed diagonally and it is in contact with the positive plate. K2 is and K1 exist on the left hand and right hand side of the gap, and here K2 may be greater than K1 or vice versa. K2 may be greater than K1 or vice versa. That means K1 may be greater than K2 also. Now, in another case where the dielectric medium of dielectric constant K1, is placed in the left portion, and this is the dielectric medium of dielectric constant K1 which is placed in the left portion, and another dielectric medium of dielectric constant K2 is placed in the right portion. K1 is placed in the left portion. K1 of dielectric medium of dielectric constant K1 is placed in the left portion of the gap between the two plates diagonally. That means this dielectric medium of dielectric constant K1 is in contact with the positive plate. In the last case, K2 was placed is in contact with the positive plate, but here K1 is in contact with the positive plate, or it is placed in the left portion of the gap between the two plates. K1 is the dielectric constant of the medium which exists in the left portion, of the gap. In the last case, K2 was the dielectric constant of dielectric medium which was placed in the left portion. In this case, C is equal to Q1 K2 divided by K1 minus K2 divided by K1 minus K2 divided by K1 minus K2 bracket closed, epsilon 0 A divided by D log base C or ln K1 by K2, log base C or ln K1 divided by K2, So C is equal to K1 K2 divided by K1 minus K2 epsilon 0 A divided by D, and here this is the dielectric medium of dielectric constant K1, and in the denominator we should have K1 then minus K2, and K1 by K2. K1 should be divided by K2 if K1 exists in the left portion of the gap. And similarly, if K2 exists in the left portion, in the denominator we should have K2 minus K1, and in the log function we should have K2 by K1. C is equal to K1 K2 divided by K1 minus K2 epsilon 0 A divided by D log base C K1 by K2. If K1 exists in the left portion, K1 exists in the left portion of the gap between the two rectangular plates. So in the denominator we should have K1 minus K2. But in the last case, and here and here in the log function we should have q1 by k2. But in the last case, k2 exists in the left portion. In the denominator, we should have k2 minus k1. And in the log function, we should have k2 by k1.